our experiments. All right, you want to randomize your experiments. We looked at one last time, the completely randomized design. There are two others that are a bit more complicated for us to take a look at. But first, let's talk about the completely randomized design. All right, so remember our Coca-Cola experiment where we want to know, does drinking a Coca-Cola increase your heart rate? And so we talked about a lot of the issues with that. It could be the sugar, it could be underlying health issues, nervousness, anxiety. There could be all kinds of things that could affect our results. So what do we need to do? We need to control things, all right? We randomly put people into groups, and we try to do a bit of control by having a placebo, essentially, which is our caffeine-free soda, and we're going to compare that to our regular soda that has caffeine, randomly put people into those groups, and then see, does our heart rate increase? I think this would be actually fun to do if we ever actually meet in person as a class. It'd be a pretty easy experiment to do, and we could see, is it the caffeine, is the sugar, what happens here? It'd be pretty fun. Someday, ladies and gentlemen, I predict January. I might be a bit optimistic, but I predict January. All right, so some popular questions to ask that I'm hoping you could talk about and elaborate on at some point. Why do we need the control group? All right, this is one thing you want to be able to articulate. Why do we need the control? Remember, our control group here is the caffeine-free soda. All right, so we want a control group. And a good buzzword to use here is the word baseline. To get a baseline of comparison. All right. A control group gives you a baseline for your comparison. That way we have a group that has a similar experience to our other treatment group. But use that word baseline in there. That really helps. All right, why do we randomly assign people to the groups? That's another thing you should be able to elaborate on. Why do we want to randomly assign people to group caffeine versus group no caffeine? Well, you guys had a lot of issues. You were able to tell me a lot of issues with this experiment, and the random assignment takes care of those issues. All right, this creates, in this case we have two groups, right? This creates two groups that should be roughly the same. Now, I'm not talking numbers, all right? It's easy to make a group of 10, a group of 10, or a group of 15, a group of 15. I'm not talking numbers. I am talking other variables. All right, this means other variables that might affect our results. Some of the things you came up were anxiety, caffeine tolerance. All right, all of those will be evenly distributed between our two groups. And so if our two groups are roughly the same, then we are hopefully mostly measuring just the difference the caffeine is making. All right, so these are two popular questions right here. Why do we need a control group? There we go. And why do we randomly assign people to the groups? Two questions you want to be able to elaborate on for actually any of these designs that we're going to take a look at. That one's probably the simplest, the completely randomized design. Two good options there. Use a calculator to randomly put people places, or write some stuff down on a piece of paper, put the paper in a hat, shuffle it up, and have everybody pick a piece of paper out of the hat is another common, easy way to describe how to randomly assign people. All right, time for some new stuff. You ready for this? Blocking and randomized design is our first one. All right, put that down in your notes. Make it nice and bold the way I did. Our first, more complicated way of randomly assigning people is called blocking, or randomized block design. Now, this is going to sound familiar because we've kind of done this with samples, but it has a different name. So you block subjects into groups that have something in common, something that might add variability to your experiment. So before you even do the experiment, you take a look at your sea of volunteers and you're like, wait a minute. I see some of you are similar in certain ways. I'm going to group you over here. You are all similar. I'm going to group you over here. And then I'm going to run my experiment. That should sound familiar. We did that with stratification with our samples and our observational studies last week. All right, remember strata? You group surveys into different groups based off of something similar. And what does that do? That decreases variability. Which reminds me, I got your homework graded from last time, and so I have some results from that I would like to show you. Where is my dot plots? There we go. So, if you remember our the corn crop problem that you were doing for homework, I have third period's data. I haven't put all the other periods with it yet because I haven't gotten them graded. But here is the dot plot for the average corn yield for your when you all did this is the simple random sample. So the actual average was 50 something. I think it was like 50.4. Like the actual average was 50. And this is your results from your simple random sample. Okay? Then these were the results from your stratification when you went vertically. You picked one plot in every column. And this is the best one, actually. Take a look at how close all of your dots are to the actual value. The actual value was like 50 point something, I think. And everybody's dots are so close to the actual value. And then stratifying horizontally, if we take a look at that, only 16 people got me the numbers. A few more people did the homework assignment but didn't give me the numbers. And there were a lot of zeros on this one. I'm not going to lie this time. You might want to get that into me. But take a look at the horizontal one. That was not much better at all. Still very spread out. Now, the spread is sort of centered on 50. This is true. All right, 50 is still kind of the middle. But it's very spread out. So stratifying horizontally didn't really help us. That was just more of a thought exercise because there was nothing similar horizontally going on. Oh, you want to send that to me. I did want those numbers. All right, there's nothing similar about those crops horizontally. There was something similar about them vertically. So we never should have done the horizontal stratification, but it was good practice. The vertical stratification, they had something in common, how close they were to the river. And so when we did it that way, that reduces the variability a whole bunch. And you can see we are super clustered right here at around 50. Compared to our simple random sample, 50 isn't even really the center anymore. Oh, this one, yeah. So I was grading the simple random sample, and I was like, why do so many people keep getting 33.7 for their simple random sample? Why do they keep getting 33? And I was like, those cheaters, they were just copying off each other. Ah. And then I was like, wait a minute. All right, I'm going to give them the benefit of the doubt. Maybe I shouldn't, but I'm going to. Random numbers are actually really hard to get. It is hard to make something truly random. And the random button on your calculator is not perfectly random, actually. And so if 1, 2, 3, 4, 5 people or so, if you all had turned on your brand new calculator and you had never done a random number before on your calculator, like you pull out brand new TI-84s, and if you both go to random integer and you say generate a random integer, they will give you the same one. All right, they use the clock, the internal clock or something inside the calculator, and it does some weird algorithm that's pretty good at random. But if you get two brand new calculators and you start them at the exact and sort of do the exact same, or their first random integer will always be the same, sadly. So I'm guessing that's why I had this many 33.7s. All got the same one. So calculators are not perfect. Random is actually kind of hard to get true random. But this benefit of stratification, where we have less variability because we grouped fields that had something in common, also happens with experiments. Okay? Now, we can't call it stratification. That's the important thing. Stratification is observational studies, surveys. But if you do that same principle for an experiment, we call it blocking. Okay? We call it blocking. So we really got to try to get that vocabulary straight and separated. But it is a very similar idea. So I got an example that will show you why this is important, what it does for us. It's a little dated, but I had graphs for it, so it shows the concept really well. So a cell phone company has designed a new keyboard, and they want to test if people can type faster with it compared to the old keyboard. All right, fair enough. 10 volunteers were randomly assigned to either keyboard A or keyboard B, and all of them typed the same passage. The results of their typing speed are shown below. Fun fact, actually, did you know our keyboard that we use on your laptop is designed to make you type slower? All right, back in the day of typewriters, when you actually had the big arm smacking a ribbon to put ink on it, they had to slow people down because they were getting jumbled up and they would get stuck. And so that's where our keyboard comes out of, is trying to get you to type slower. There were keyboard designs designed to make you type faster, where the most used keys were actually on your fingers, but people could type too fast, and it would gum up the typewriters. And so they switched to the one we have right now, the QWERTY keyboard, as it's referred to, because at the top left it's QWERTY, QWERTY. Fun fact, the more you know. Da-na-na-na. Wake up. All right, so they randomly assign these people. 5 of you go to keyboard A, 5 of you go to keyboard B, type it out, and there are our results. And if you look at that, it's kind of inconclusive, right? I mean, A kind of looks better, but not really. I mean, look at this overlap. The lowest one for A, the lowest one for B, the highest one for A, or B, the highest one for A. But most everything is right here in the middle. There's a ton of overlap. We don't really see any difference here. So there's not really enough evidence to say, hey, A is better than B. There's just too much overlap. They look too similar. But then, Bolt comes in. In the waiting room, Mr. Bolt saw that all the participants were on their phones. Only 4 of the participants had smartphones, while 6 of them had old flip phones. Oy, oy, oy. This must be like 2005 or something. Gasp. Cell phone proficiency is adding a lot of variability to our data. All right? We cannot compare these apples and oranges. We shouldn't necessarily compare people that have smartphones to people that don't have smartphones. That could really affect your typing speed. To date myself, here's another funny story. I was pretty young, because I don't know if I was watching this show willingly, but I was watching Rosie O'Donnell's talk show, and she had a race between somebody texting, like on an old 10 key, whereas you just had to do 1, 2, 3, 1, 2, 4, 5, 6, 7, 8, 9. That's all you had. Versus somebody doing Morse code. And they had the race to see who could win. The Morse code person or the old text. You probably never even texted the old way, did you? Where you had to go click the 1 button 3 times to get to the C. Go A, B, C on the 1 button. You don't even know what I'm talking about. I hate you right now. Did you? Have you? Yes. Yeah. Oh, that's cool. Yeah, those were the days. Those were the days. Back when you had like 20 texts that you could send in a month, and that's all you got. Yeah, good times. All right, so what we're going to do here is we can't compare these apples and oranges directly together. It's not fair. It's not going to help us to put them all in one basket. All right, we got to separate the oranges, compare the oranges. We got to separate the apples and compare the apples. Then our data will look better. That is called blocking. When we separate people by how they are similar. So I'm going to draw a quick diagram for you for what this looks like. So we have our 10 volunteers here, right? So what we're going to do first is separate these people out. All right, this is not random. We are blocking right here. So we're going to put our 4 smartphone users up here. And our 6 dumb phone users down here. All right, we're separating them out because we know they're different. And that is not random. All right, we do that purposefully. But we have to do something random. So what we now do is each of those blocks, we now do a random assignment in each block. Random assignment. All right, random assignment. So within these 2 blocks, let's see, for the first block, all right, 2 volunteers will get keyboard A, and 2 will get keyboard B. Whoa, keyboard. And then for our other block, let's see, we have 6 users, so this time it'll be 3 and 3. 3 will get keyboard A, and 3 will get keyboard. Man, I cannot spell keyboard today. Who would have known? O-A-R-D, keyboard B. And then we run the experiment based off of those. But that's kind of how blocking works. You first separate them out by some similar characteristic they have. Then within those blocks, you still do a random assignment. All right, so how would we do this? We would probably use a simple random sample, all right, an SRS, to divide them up inside their blocking. All right, and what that does for us is it eliminates a lot of the variability, and we'll be able to see, hey, is there a difference between keyboard A and keyboard B? So with this great fake data, here's what we get. All right. So all that's happened here is they've coded the smartphone users as red. So take a look at our 2 smartphone users from keyboard B. And now we're only going to compare them to the other smartphone users of keyboard A. And take a look. That looks like a pretty good increase. All right. Both keyboard A users went faster than the keyboard B users among smartphone users. And among non-smartphone users, it's a very similar story. There's a little bit of overlap, but only 1 point overlaps. The other 2 fall into this idea that keyboard A is in fact faster than keyboard B. All right, so what do we see? Overall, keyboard A users were faster typers than keyboard B users and I might add in their block. Now, that's not the only way to describe or show that data, all right? They do something kind of fancy here in the book, is they combine the data. All right, instead of having the red above the black, what they did was, this is kind of fancy. I'm not sure how important this is, but it could happen. So the average speed for a smartphone user was 40 words per minute, while the average speed for a non-smartphone user was only 26 words per minute, okay? Which is a difference for 14 words per minute, all right? So that means on average, a smartphone user is 14 words a minute ahead of a non-smartphone user. Well, what we can do then is we can subtract 14 from not all cell phone users, from all smartphone users. All right, subtract the 14 from all smartphone users to even the playing field. So we're turning the apples into oranges by subtracting 14. We could have gone the other way around. We could have turned oranges into apples by taking the dumb phone users and adding 14. All right, it's kind of like a golf handicap. I'm sure we all know about golf handicaps, right? I don't play golf. But that evens the playing field, so then we can actually combine the data. All right, so here is our combined data for blocking here. So now the red points are mixed into the black points, but you can still see in general there is a marked increase from keyboard B to keyboard A. I would hope keyboard A was their new design. They never actually said which one was the new design. Maybe the one they had is actually worse than what we usually had. But there is a marked difference there between A and B there, even when you combine the data. And so if we compare that, all right, here is our blocked data compared to just the simple random sample. And with a simple random sample, we can't really tell that one is better than the other. There's just too much variability. All right, there's too much variability, but when we block people by something they have in common, it gets rid of one layer of variability, and therefore we can see our data, what our data is trying to tell us much more clearly. Okay? So, what happens here? What does blocking really accomplish? Blocking allows you to account for one level of variability. All right, or one or more, I guess, if you block by more than one thing, one or more levels of variability. So it is easier to see if the treatment, whatever it may be, whatever the treatment may be, has any effect. So we were able to get rid of cell phone proficiency, or I guess, well, maybe not proficiency, but the type of cell phone you use as a level of variability. We were able to get rid of it. So the motto is, I like this, control what you can. All right, if you can control it, control it. Like we controlled sugar for our Coca-Cola experiment. Well, I didn't mention this at the beginning. What did they control in this experiment with the cell phone typing? They did control something. If I go up to the actual darn problem, where is it? There it is. What did they control? They all typed the same passage. All right, could you imagine if they gave them different things to type? Well, you gave us a whole bunch of special characters. I had to type the percent sign, man. What the heck? Whereas the other group didn't. That would be a variable that you would add in. You don't want to do that. So they controlled the passage there as one example. So you control what you can. And then you block what you can't control. All right, I can't control if you are a smartphone user or not, okay? But I can block by it. That will help get rid of the variability. Control what you can, block what you can't, then randomize to create groups that are similar. All right, even after you block, are people still going to be different? Oh yeah, they're still going to be different. And so you randomize who's in what group to hopefully take care of those other variables that you can't block with. All right, there it is. All right, so we're going to do one more example of this. This is kind of a complicated one. With our Coca-Cola experiment. All right, we're gonna pretend that you all are our subjects, and I'm gonna block you for this experiment. Now, one thing we thought might be an issue. I'm getting my chat up here because I'm gonna put a poll in the chat here. All right, one issue we thought might be a problem or a variable with our Coca-Cola experiment is caffeine tolerance. All right, some people drink tons of caffeinated soda or coffee or anything that has caffeine. Some people don't drink any of caffeine. That would add variability to our experiment here. Now, hopefully if we did randomized grouping, yes, we would assume that those types of people would be evenly distributed. But if we blocked our experiment, we could account for that variable at the beginning. So I'm going to poll you all right now. How can I do that? There. I need to add a form. I'm going to ask you, how many caffeinated beverages do you drink a week? Do you drink a week? All right, so your first option is usually none. Your second option is, I don't know, somewhere between 1 to 3. Now this includes coffee or soda, anything, and then the last one is 4 or more. I think it's this one I have to click. There we go. So there are my 3 blocks. Let me know. How many caffeinated beverages do you drink a week? Coffee, soda, anything. Usually none. 1 to 3, 4 or more. Be honest. How many of those caramel frappuccinos do you get from the Starbucks every week? And then drink all 800 calories of that cream in there. Oh my goodness. All right, what do we got here? That's 1925 people. That's how I get through school days. A monster. I once had a student try to drink a 5-hour energy, like right when they came out. Like this was a long time ago. 5 hour. He's like, I'm tired, but I'm gonna get this. And he threw it back. It's a little shot, right? And then he ran to the trash can and just like threw it up because it tasted so gross. I was like, man, that's too much. All right, what do we got? We got 26, 27. All right, let's call it there. All right, so I have now blocked our class into 3 blocks, okay? Because I think caffeine tolerance might change our results. So we've got, how many, 10, 20, 27 volunteers. 27 volunteers. I'm going to diagram this out. So I have 10 of you up, 11 of you with no caffeine. So 11 no caffeinated beverages. And then I have 10. Oh, now I'm at 12. Oh, man, you're killing me here, guys. 10 that drink 1 to 3 a week. And I've got 6 people with 4 or more. Now, that is not random. I'm looking at you all and I'm saying, hey, how are you similar or not? And I'm grouping you by that. Now, this is the same category. I can't create multiple categories here. It's all about how many beverages do you drink. I can't also somehow start putting in health issues, right? That's a different category. I can only block one sort of category of idea right now. But then from there, I now randomly assign everybody to what group they're going to be, all right? Randomly assign. Randomly assign. You still have to have a random assignment. So I'm randomly assigning you to either, oh, we did red and blue, wasn't it? Red or blue. One of them having caffeine, one of them having no caffeine. Oh, do we have all even numbers? Sweet. So I will randomly assign 6 people here to red, 6 people here to blue. I'll randomly assign here, I get 5 and 5. And here I'll get 3 and 3. And then we'll see, what difference does drinking 1 soda do to your heart rate? And it's very possible we'll see that, whoa, your heart rate is crazy increasing in one block, but not in the other. And then we can say that, that happens. Or we can see a little bit of increase in all of yours. But if we put all the data together, it'd be so variable that we might not see the changes that are happening because some people, I'm guessing the people down here, will be much less affected than the people up here. And if we combine their data, we wouldn't see the fact that everybody was increasing a little bit. All right. So that is blocking. It's a very important aspect. Again, control what you can, block what you can't, randomly assign for the rest. Then your groups will hopefully be somewhat similar. All right. Whew. What are we? We're at 11 o'clock. Jeezum. I do want to talk about matched pairs. Stay with me here, ladies and gentlemen. That was long, I know. That's a complicated. Usually we would spread this out over like a day or two, but
I'm sorry too.
We gotta knock it out. I'm gonna say hi to everybody's family there who's listening in the background. All right, so matched pairs is our last one. This one isn't too complicated, but it kind of has two subgroups to it. Pairing similar subjects and giving both treatments to each subject. So again, let's take our Coca-Cola experiment as our example. Ooh, that's getting a little too loud for me. I'm gonna go ahead and mute you there. Sorry. I'm not trying to be rude. All right, so what we do for a matched pairs is you create pairs. So the first way is I'm going to take two people that are similar and then randomly assign them the treatment. So first, take the two people who consume the most caffeinated beverages. All right, so I'm going to take the top two. So I would have to do another survey and actually ask, how many do you all do? And I'm going to take the top two and randomly assign red can and blue can, the treatment. So I take the top two people in the four or more. I'd ask you, hey, how many do you? I do 10 drinks a week. I do 9 drinks a week. You two are pretty similar. So I'm going to take the top two people for consumption, and I'm going to give them a randomly assigned. Then the next two who drink the most. And randomly assign treatment. Hopefully you can see the pattern. And so on. All the way down. All right, I'm taking the two people that did the most, I'm pairing them together and randomly assigning treatment. Then I take the next two and randomly assign the treatment. Then I take the next two and I randomly assign the treatment. And the next two, and the next two, and the next two, and the next two. Pairing you all together with whoever is near you in terms of soda or caffeinated beverages that you drink a week puts you in a group of two that are very similar, and then I can track each group individually that way. All right, that's the first way of match pairing, where you pair people that are similar. Now, you could also pair in another way. That's where you give both treatments to each subject. So maybe day 1, you'll get the first treatment, and day 2, you'll get the second treatment. All right, so first, everyone. Wait, does this one work? You would have to stay there and then. Yeah, first everyone randomly chooses, like flip a coin or something, randomly chooses a treatment. All right, so we can't all do red can, then all do blue can. You do have to randomly choose one or the other. First, everybody randomly chooses a treatment. All right, then we would measure pulse before and after. Then, let's see, for this one, it'd have to be like the next day. It doesn't always have to be the next day, but then the next day, everyone does the other treatment. So you personally are going to do both, but you have to do it in a random order. Because if everyone did the same order, there might be some issues that arise with our other confounding variables by always doing the soda with caffeine first and the soda without caffeine first. Maybe the second time you were ready for it, and you're like, I'm going to deep breathe so that my pulse rate doesn't go up. All right. And there could be weird things like that if we all did it in the same order. And you don't want that to crop in. But it's still a matched pair because you're doing both. All right. You're doing both. You're sort of pairing both treatments to yourself. And that's not a great way of talking about it, but there it is. All right. So those are our last treatments. We got 3 now. You could either completely randomize who goes where, which is good. It's simple. It's quick. It is used a lot, but it can sometimes have a lot of variability. So what do? You group people by a way that they are similar, a block design. All right. If it works, it is sometimes even better to do a matched pair design where you have a whole lot more groups. All right, you pair people up or you give the treatment to both people and compare their results to themselves. It gives you much clearer data because everybody is given both treatments. Not always possible, but it is better results for you. These two, lower variability. All right, lower variability. It is easier to see the effect of the treatment. All right, I'm going to stop there, ladies and gentlemen. That gives you kind of intro to all of them. The video, I'm going to go over a few more examples of these. It's not going to be a new topic. I'll do a few examples. I'll probably end up getting some homework problems and going over those so you can see a few more examples of probably the second two, not so much the randomized one at the beginning. That was pretty easy, but the blocking and the matched pairs. After you watch that video, you should hopefully be pretty good on your homework problems. But I'm hoping that gives you a good intro, ladies and gentlemen. Whew. That was a lot. I'm tired. You tired? I'm tired. Go drink a caffeinated beverage. And you'll wake up. All right, everybody. That's 10 minutes early. You deserve it. Go take a nap. Just don't miss 5th period. Have a good one, everyone. Come by office hours if you got questions or concerns. I know you want a Starbucks. We all want a Starbucks. I make my own coffee, though. Have a good one, everyone. I will see you on Friday. Oh, so far yet so close. I'll see you Friday.
Mr. Bolt,
Go for it.
are you going to upload this to homework 19? Like make it an assignment or no?
Oh, yes. I don't think I've created homework 19. This will be 19?
Yeah, I think so.
Yeah, I think it's 19. I have not done that yet. It
And
will
when
happen.
is this due? Is it due